Hello, thanks so much for attending this presentation. My name is Javier Robledo Moreno, and I'm a research scientist at IBM Quantum. And today I'm going to be discussing the fundamentals and applications of sample-based quantum diagonalization. Sample-based quantum diagonalization is a hybrid quantum classical technique that allows us to study the eigenstates and eigenvectors of quantum many-body systems. The goal is going to be to solve a computationally challenging energy estimation problem with applications in quantum chemistry and material science. And in particular, some of these applications is going to be the development of new materials, drug discovery, battery design, you name it. Previously, there's been some proposals for algorithms to tackle these problems. In the fault-tolerant regime, the very famous quantum phase estimation algorithm is one of the most prominent proposals, where one can guarantee that the algorithm will converge to the exact solution, provided that we can prepare an initial state in the quantum device that has 1 over a polynomial overlap with the true ground state. However, some of the key requirements is that it requires very deep circuits and fault-tolerant quantum processors. More algorithms, but better suited for near term to address these types of problems is what we call variational quantum algorithms, which in this case do require usually shallow circuit depths. However, some of its key challenges is that they do not have convergence guarantees, so we cannot guarantee that they will give us the right solution. And for example, for chemistry problems, they face pretty significant measurement overhead challenges. This means that whenever we want to estimate the expectation value, in particular of the Hamiltonian, we will have to spend a lot of time collecting samples from the device to estimate the expectation values. And sample-based quantum diagonalization is a proposal put forward to try to address these issues. So let's begin with a little bit of a more detailed problem statement and eigenstate approximation. What is it that we are trying to do? So we are trying to find the eigenvalue and eigenvector pair of an exponentially large matrix, which is what Hamiltonian. In particular, we are trying to find the eigenvector corresponding to the smallest eigenvalue of this matrix. This is what we call the ground state. And the eigenvalue is what we call the ground state energy. As I mentioned before, this vector space has a dimension that is exponential in the system size. And here the system size can be characterized, for example, by the number of electrons that you have in your molecule. However, something that we also know about these Hamiltonians that live in exponentially large Hilbert spaces is that for the typical many-body problems that we are interested in, these matrices are exponentially sparse. This means that even though they have exponentially many rows and columns, the number of non-zero matrix elements, for example, per row or per column, grows polynomially with the system size. Here, I'm just writing one of these, let's say, a representation of one of these exponentially large matrices spanned in a basis of bit strings or computational basis states in a Hilbert space of n qubits. Now, for some of these physically relevant or chemically relevant problems, we're gonna use an additional assumption, and is that we're gonna assume that the eigenvectors of interest to us are going to have polynomial support. That means that an exponential number of its components are going to have orders of magnitude smaller amplitude as compared to the dominant dimensions in this Hilbert space. And let me try to illustrate why this intuition might make some sense. Let's, for example, consider a system where, we have, let's say, 3 atomic orbitals and 2 electrons that are available to occupy these 3 atomic orbitals, and they are ordered according to their energies. If we want to describe the lowest energy state of this system, well, intuitively, it makes a lot of sense that these two electrons are going to be mostly occupying the low energy orbital, whereas higher, so the occupancy of higher energy orbitals leads to corresponding smaller wave function amplitudes. So this intuition, these observations, allows us to remove dimensions in this Hilbert space that may not be as relevant for the description of the ground state. And imagine that we do a thought experiment where we are given the relevant dimensions of this Hilbert space. What we can do is we can project this exponentially large matrix into the subspace of the relevant electronic configurations in this case to describe the ground state, and we can perform a diagonalization in a subspace that is significantly smaller and therefore is a tractable diagonalization problem as opposed to the diagonalization in the exponentially large Hilbert space. Now the problem becomes the identification of these less relevant dimensions, or the identification actually of the relevant dimensions of our Hilbert space. On the classical side, there exist tree-like search methods that go under the general umbrella of selective configuration interaction that rely on heuristics or physical intuition and perturbation theory to perform the selection of the relevant degrees of freedom of the problem. Usually, the way that these methods work is that we begin by an approximation to our ground state in a much smaller subspace. We augment the number of dimensions of this ground state vector by the application of the Hamiltonian. Then we rank the corresponding dimensions or electronic configurations. We are going to select them according to some criterion, and afterwards we perform the diagonalization in the resulting subspace, and we repeat this procedure iteratively until we converge. Now, on the quantum side, we have sample-based quantum diagonalization, where we're going to be using a quantum circuit, here denoted by psi, which upon measurement in the computational basis is going to be in charge of identifying the relevant degrees of freedom of the problem, the relevant electronic configurations or determinants. So as I mentioned before, the measurement procedure of this quantum circuit is going to define a probability distribution over the Hilbert space, and we're going to be taking the electronic configurations, the bit strings, the computational basis states that are sampled more often to define the subspaces where we're going to project the Hamiltonian to and then diagonalize it in. But as with any type of quantum processor, we need to deal with effects of quantum noise. And we're going to do so with something that we call configuration recovery. This procedure of collecting samples from a quantum device and then projecting the Hamiltonian and diagonalizing it in the subspace has some inherent resilience to the effects of noise. Let's consider this very simple toy model where the ground state that we want to find is the linear superposition between the 1100 state and the 0011 state. For example, this could correspond to a 4-orbital molecule with 2 electrons in it. Now, let's say that these are the 3 bit strings that we sampled from our quantum device, 0011, great, that was part of the support of the ground state, 1100, which was also part of the support of the ground state, but let's say that because of the effect of noise, we're also sampling the bit string 1010. What we're going to be doing is we're going to be projecting the Hamiltonian into the subspace. So this means I'm just going to be computing the matrix elements of these bit strings or these computational basis states with the Hamiltonian. I'm going to form this 3x3 matrix. In this case, you can see that if I have 4 qubits, technically the Hamiltonian would be 16-dimensional, but I'm here since I only need 2 of those computational basis states to describe the ground state. I'm going to be working with a reduced Hilbert space. This is the Hamiltonian projected into the subspace. Now, upon diagonalizing the Hamiltonian in the subspace, what the diagonalization subroutine is going to do is going to assign non-zero wave function amplitude to the computational basis state A, which was indeed in the ground state of the problem, and also a non-zero weight to the computational basis state C. And however, is going to simply assign zero weight to the basis state B because it does not participate in the description of the ground state. So to this extent, the diagonalization procedure can filter out those bit strings that actually do not participate in the description of the ground state properties of our systems. However, we wonder whether we could do even better than that, whether we could use some physical intuition to deal with effects of noise even further and improve the efficiency of the method. Because something that you might observe is that if you only rely on the diagonalization to filter out the bit strings that do not contribute to the ground state, you may end up having to perform very expensive diagonalizations on subspaces which are much bigger than the ones that you need to characterize your system. Therefore, we came up with something that we call self-consistent configuration recovery, and it actually has a very simple intuition. Let us go back to our 4-qubit previous example where, it was describing a system with 4 orbitals and 2 electrons. Now, imagine that because of the effect of noise, I receive one computational basis state from the quantum device that is missing 1 electron. That is very easy to identify because its Hamming weight will be wrong, right? Here we are expecting that this bit string should have an extra 1 in it. And also, we can also exploit another property of these systems, which is, on average, how many electrons do we have on each orbital? This property is a property of the ground state itself and is something that can be measured. So let's say, imagine that we know what these average orbital occupancies are, and let's say that, for example, for this orbital, we expect a high occupancy. For this other one, we expect also high occupancy, but for example, for the last one, we expect pretty low occupancy. And remember that we want to flip one of these zeros back to a 1 because we know that we should have 2 electrons. Well, which 0 will I flip? Well, I will flip this one with higher probability because I know that on average there's more electrons on the corresponding orbital. So we'll do some probabilistic bit flipping to recover the correct number of electrons or particles based on the average orbital occupancy. So the probability of flipping a bit is given by the difference between the value of the bit and the average orbital occupancy for the corresponding orbital. And as I mentioned before, these average orbital occupancies are just some expectation value of the ground state itself. Now you may wonder, okay, but in principle, you do not know the ground state because that is what you're trying to find. So how can you compute these average orbital occupancies? Well, we actually don't assume that we know them a priori, but instead we're going to compute them and refine them self-consistently. So let me show you what the workflow for that procedure looks like. So the very first thing that happens, as I mentioned before, is that we prepare a quantum state in the quantum device psi, and we're going to collect a set of measurements in the computational basis. These measurements are going to come to us in the forms of bit strings of length n. N is the number of qubits of the problem. And as I mentioned before, a critical property of these bit strings is the number of 1s and 0s that they have, because the number of 1s corresponds to the number of electrons. These bit strings represent electronic configurations of our problems. Now, the set of noisy bit strings, they are going to get passed into the classical post-processing part of the algorithm, where at the very first iteration, we're just going to do post-processing. We're going to ignore the bit strings that come with the wrong number of electrons. We're going to do some bootstrapping. We're going to subsample them according to the empirical frequencies with which they appear. And we are going to run this projection and diagonalization in the subspaces spanned by the different batches of samples. Once we have done that, we have a first approximation to the ground state, and therefore we can compute a first approximation to the average orbital occupancies. This information will be passed back to this configuration recovery step where we do this probabilistic bit flipping of the measured outcomes from the quantum device. And we will go back into doing the bootstrapping of our samples, sending them through the projection and diagonalization. And at this stage, we're going to be obtaining a more refined version of the ground state, and therefore a more refined version of the average orbital occupancies, which we can send back to configuration recovery and loop self-consistently until we observe convergence, for example, of the ground state energy or other ground state properties. And here it is important to note that the most computationally intensive part of this workflow is the projection and diagonalization in the subspace. This is one of the demonstrations of something that we call quantum-centric supercomputing, where quantum and HPC, high performance computing resources, work together to produce interesting simulations of physical systems. But let's try to quantify how well this self-consistent configuration procedure works. And for that, we're just going to run some numerical experiments. We're going to consider the dissociation of the nitrogen molecule, and we're going to consider 24 different bond lengths. And we're going to assume a very simple noise model, okay? We're going to say that the probability of measuring each of the bit strings, the noisy probability, is going to be some parameter alpha times the noiseless probability of sampling the bit string, and 1 minus alpha times the uniform distribution, okay? So here alpha represents the amount of signal that we have in this simple noise model. Here on the y-axis, I'm showing the energy error, because remember, we are trying to quantify the ground state energy. So the energy error relative to the noiseless case, here as a function of the amount of signal that we have. And this would, again, simulate what would happen with a quantum device. The green points correspond to the energy errors that we would make if we didn't do configuration recovery, if only we just post-process the data, if we completely ignore the electronic configurations that came with the wrong number of electrons. And we see that in order to get errors in the order of 10 millihartz, well, an amount of signal of greater than 20% suffices to reach that threshold. Now, if we pay attention to these brown points, these are the energy errors that we obtain if we perform this self-consistent configuration recovery procedure on the same data. And we see that the energy error is not only significantly lower, but also something that is important to remark is that in order to reach the same 10 millihartz threshold, instead of requiring 20% amount of signal, now we require just 2% of signal to reach the same level of accuracy. So configuration recovery is indeed a key part to this sample-based quantum diagonalization workflow. Now, something that I have not discussed so far is the quantum circuits. Where do we get the quantum circuits from to produce samples that are going to be defining the support of the target eigenstate that we're after? Well, so that we have two choices. The first one is heuristic choices. We can use physically inspired ansatz, and what we have been using so far for electronic structure problem is something that is known as the local unitary cluster Jastrow circuit, which can either be optimized to minimize the variational ground state energy estimation coming from the sample-based quantum diagonalization workflow, or we can initialize its parameters from approximate classical electronic structure methods. This is what we have been calling sample-based quantum diagonalization. On the other end of the spectrum, we can construct some classes of circuits that have provable convergence guarantees. So, and in particular, that is going to be sampling from members of a Krylov basis. We also know that time evolution circuits can be pretty hardware friendly circuits, and they also form Krylov bases. However, this latest class of circuits may not be very well suited to describe ab initio Hamiltonians, or directly molecular Hamiltonians. This is because the number of terms on these ab initio Hamiltonians grows as the number of qubits to the fourth power, which leads with a very large number of quantum gates to be implemented in the quantum device if we want to implement the time evolution. Sampling from members of a Krylov basis is what we call sample-based Krylov quantum diagonalization, SKQD in short. So let's first discuss these physically motivated classes of circuits, the local unitary cluster JASTO. When it comes to coming up with variational circuits, there are two different very separated classes of circuits that we can think of. The hardware efficient ones, which are compatible with hardware. They require low connectivity, a relatively small number of gates and depth. However, these classes of circuits are known to be hard to initialize and to optimize. And in the other end of the spectrum, we have the physically motivated ansatz, which can take parameters from classical calculations, and they tend to be easier to optimize. However, they require all-to-all connectivity, high circuit depth, and gate counts. The local unitary cluster JASTO circuit tries to find a middle ground between the two. It takes physical motivation derived from unitary coupled clusters and hardware friendliness by imposing device-specific connectivity. So let's see, where does the local unitary cluster JASTO come from? It comes from unitary coupled cluster with singles and doubles, here where we have the exponential of the cluster operators. Now what we are going to do is we're going to expand the cluster operator as the linear combination of some density JASTO terms. This is some diagonal two-body terms sandwiched between orbital rotations of the following form. This leads with a circuit structure which is the product of layers of orbital rotations that surround a density time evolution. The orbital rotations are hardware friendly and require linear connectivity to be implemented. And these density interactions, in principle, to be able to exactly match unitary coupled cluster ansatz, should be all-to-all. And here the approximation comes from restricting these density interactions to only be applied to qubits which are physically adjacent in the quantum processor. Some properties of the circuits is that they can take input as input parameters the results of classical approximate electronic structure calculations, and in particular from coupled cluster theory. This is what has been done for these classes of circuits so far. There is evidence that they can perform better than their classical counterpart. In some limits, these circuits, we believe they are hard to simulate classically because we don't know any methods to simulate them. And they are, as I mentioned before, compatible with quantum hardware connectivity. Now, on the other end of the spectrum, we have this sample-based Krylov quantum diagonalization, where the only thing that is changing is the circuits that are going to be producing the samples. And as I mentioned before, we're going to substitute this local unitary cluster JASTO circuit with time evolution circuits, two different time slices. So the idea is that we need to prepare a reference state which has good enough overlap with the target ground state that we are trying to find. And then we're going to do time evolution of that reference state to different times. And at each of those times, we're going to collect samples from the quantum circuits, which, again, they're going to be representing electronic configurations or relevant degrees of freedom for our problem. The very nice property of sampling from a Krylov basis is that provided that we have an overlap of the reference state that is 1 over some polynomial in the number of qubits with the true ground state, that the gap doesn't vanish exponentially, and that we have a sparse ground state, we can prove that the ground state error converges efficiently with the number of circuits and samples. These first two conditions come from standard Krylov approaches, And the second condition comes from sample-based quantum diagonalization. So now let's move into some of the applications that we have been studying at IBM. And we're going to begin by describing the application of sample-based quantum diagonalization to the search for the ground state properties of electrons in molecules. We studied 3 systems. The first one is the dissociation of the nitrogen molecule in a correlation consistent basis set. This is a 58-qubit experiment. Here you can see the qubit layouts that we used for these experiments. In red, you have the qubits that correspond to the spin-up orbitals. In blue, you have the qubits that correspond to the spin-down fermionic degrees of freedom, whereas in green, you have some auxiliary qubits that are used to mediate density-density interactions between a spin-up and spin-down species. We also studied an iron 2 sulfur 2 cluster and an iron 4 sulfur 4 cluster corresponding to 45 and 77 qubits experiments respectively. The biggest experiment that we ran was this iron 4 sulfur 4 cluster, which is a 77 qubit experiment, and we went up to 3,500 2-qubit gates. So what are the results? Well, we studied the triple bond breaking of nitrogen, which is a fairly strongly correlated process, which is being traditionally used to benchmark electronic structure methods. Here, I would like for you to pay attention to the energy as a function of bond length curve. The black solid curve is a classical reference, and here the brown dots correspond to the results coming from the quantum device. What we observe is that the results obtained from the quantum device qualitatively describe the dissociation process correctly. Once we were successful with the description of the bond breaking of the nitrogen molecule, we moved into more strongly correlated species, and these are these iron sulfur clusters. The strong correlation in these iron sulfur clusters comes from the magnetic coupling of the electrons that live in the iron atoms. And to study their ground state properties and low excitation properties, we did something that is known as an energy variance analysis. We know that if with increasing accuracy, the energy variance, here denoted by delta H, is supposed to be approaching 0. And one can formally show that if you're close enough to an eigenstate and you have an approximate method and you increase its accuracy by turning some knob, in the energy variance plane, you expect a line that you can extrapolate to the 0 variance limit. In sample-based quantum diagonalization, the knob that we can tune to increase the accuracy of the method is the subspace dimension. The bigger the subspace dimension that we project to undiagonalize in, the more accurate the results are going to be. And this is simply coming from the variational principle. Here in the study of the ground state properties of the iron sulfur cluster, I would like for you to pay attention to the points which corresponds to the quantum points obtained from the quantum device using sample-based quantum diagonalization. The different colors correspond to different subspace dimensions. So here from yellow, that's smaller subspace dimensions, less accurate results, to dark purple, which is bigger subspace dimensions, more accurate results. What we saw is that actually when we increase the size of the subspace, we saw 3 clusters in the energy variance plane, as you can see here, which correspond to 3 eigenstates which are very close in energy to each other. This is one of the signatures of a strong correlation, eigenstates which are close in energy to each other. And what we could see is that from the extrapolation from the third cluster is that the extrapolated value to the 0 variance limit is in very good agreement with state-of-the-art classical results obtained from the density matrix renormalization group method, DMRG. Not only that, but the qualitative and quantitative behavior in the energy variance plane obtained with sample-based quantum diagonalization is in very good agreement with the selected configuration interaction methods, which is the classical counterpart that we have discussed earlier in this presentation, here shown by the crosses. So since we were successful in, remember that this was a 58 qubit experiment, this was a 45 qubit experiment, we wanted to see where were the limits of sample-based quantum diagonalization when we ran these experiments a year ago. And for that, well, we chose to go for a more strongly correlated species that had more orbitals. So that meant more qubits. So we moved to a 77 qubit experiment. And we also wanted to test the limits of the quantum processors. So we went up to 3,500 qubit gates. Now, the goal of this last experiment for this iron 4 sulfur 4 cluster is not to get a very accurate result, but instead to try to address whether we could extract a useful signal from the quantum device beyond white noise. So what we did to assess whether that was the case, we just ran sample-based quantum diagonalization in subspaces generated by completely random bit strings. Here in the energy variance plane, these are the points shown by the pentagons. As you can see, they are not aligned, which means that most likely they are not close to an eigenstate of the Hamiltonian. And we also run sample-based quantum diagonalization, but instead of on the bit string sample from the uniform distribution, on bit strings obtained from the quantum device. And those are down here in represented by the circles. And this is a zoom-in version of this small rectangle of the plot. And what we can see is that not only the energy and variances are significantly lower than those obtained by running sample-based quantum diagonalization from random bit strings, but also they're well aligned, which means that most likely they correspond to the approximation of an eigenstate of this Hamiltonian. Here, the extrapolation does not match the range of that correspond to the ground state energy, but again, however, we are somewhat convinced that they are an approximation to an eigenstate of the Hamiltonian. And as I mentioned before, this shows that we could extract a useful signal from quantum devices in chemistry experiments in a quantum circuit that had 77 qubits and 3,500 2-qubit gates. And since then, well, there's been a plethora of studies that have been using sample-based quantum diagonalization to study a variety of molecular systems, going from the interactions of two separate molecules. This is a sample-based quantum diagonalization applied to supramolecular interactions. Sample-based quantum diagonalization also applied to open shell systems. The combination of SQD with embedding methods to study larger organic molecules. And also it's been generalized to study not only the ground state properties of these molecular systems, but also the excited states of molecular systems. These excited state properties are quite relevant to understand, for example, the optical spectra of these systems. Lastly, I would like to mention that we were even able to push this method to 84 qubits and 5,000 2-qubit gates. Now let's move back into the Krylov version of the method, because all of the previous results that I have shown were obtained by running the local unitary cluster Jastrow circuit initialized from coupled cluster T amplitudes. Now, for the Krylov version, recall that what we need to do is we need to be able to run time evolution circuits for the corresponding Hamiltonians. And as I mentioned before, the Hamiltonians for molecules tend to have a very high number of terms when they are expressed as linear combinations of creation and annihilation operators or linear combinations of Pauli operators. This is why we decided that for sample-based Krylov quantum diagonalization, we were going to focus on lattice models. And in particular, we're going to focus on impurity models, What is an impurity model? Well, it's a class of models where the Hamiltonian is the sum of three terms. There is a Bath term, there is an impurity term, and there is a hybridization term. The Bath term describes free electrons in a conduction band and is diagonal when written in the momentum basis. Then we also have an impurity, which is in principle not coupled to the conduction band, and it has a Hubbard on-site repulsion interaction. That means that if I put two electrons of opposite spin in the impurity, I'm going to pay an energy price U to have them there. And lastly, there's a hybridization term that allows electrons to hop from the conduction band to the impurity mode. And it's described by something that is called the hybridization parameter Vk, and it depends on the value of the different modes. These models are very relevant to simplify real materials calculations on workflows like dynamical mean field theory, so they are not just contrived models, and they have been extensively used in the literature to benchmark numerical techniques. And in particular, in this case, for this very specific model, we know that the density matrix normalization group does a good job at describing its ground state properties, so we're going to use it to benchmark sample-based Krylov diagonalization on large-scale quantum experiments. Something else that we did to improve our results is we run these experiments in two stages. In the very first stage, we just consider the impurity models, as I described them before, in what is known as the momentum basis. In the momentum basis, we were just able to compile the time evolution circuits, and interestingly enough, the most expensive part to compile is the free fermion evolution. It is the hopping of electrons from the impurity to the bath and vice versa. This requires a brickwork circuit of Givens rotations, but since we are doing Trotter evolution of very small time slices, at the end of the day, this unitary is not too far away from the identity and can be approximately compressed into a unitary of much lower depth, and we did so variationally. After compiling the circuits, we collected samples. We ran sample-based Krylov quantum diagonalization with configuration recovery, as I described before. And then what we did is we applied a transformation to the Hamiltonian. We applied a rotation to the Hamiltonian to increase the sparsity of the ground state. And this rotation to the Hamiltonian belongs to a very particular class of unitaries that can be applied efficiently on a classical computer, and it is an orbital rotation. This orbital rotation is informed by the results that were obtained from the sample-based Krylov diagonalization running the momentum basis. And it also allowed us to efficiently compile the quantum circuits in this new basis. And once we did it, we again collected samples, run configuration recovery, projection, and diagonalization. We went up to 81 bath modes or bath sites, which means that we had 84 plus 1 qubits. 84 comes from the 41 bath modes plus 1 impurity multiplied by 2 for the spin up and spin down degrees of freedom. And the extra qubit that we used is to mediate the on-site Hubbard interaction in the impurity model. So in this case, in this qubit layout, the red qubits correspond to the spin up degrees of freedom. So all of these are bath modes, and this is the impurity mode, and these are more bath modes. The blue is the same, but for the spin down degrees of freedom. And as I mentioned before, the green is a qubit that is used to mediate the on-site Hubbard repulsion on the impurity. What are the results that we obtained from this method? Well, we looked at the relative error in the ground state energy and relative to the DMRG energy. As I mentioned before, These models have been extensively used to benchmark classical methods, and it is known that the density matrix renormalization group provides a very good baseline. And we tested a sample-based Krylov quantum diagonalization for a number of values of the on-site Hubbard interaction from u equals 1 to u equals 10. And here we are showing the relative error in the ground state energy as a function of the subspace dimension used for projection and diagonalization. A couple of things to note in these plots is that these relative errors are in the order of 10 to the minus 4, 10 to the minus 5, which means that we have very good agreement with the results obtained from density matrix renormalization group. And additionally, something that I have mentioned before is that upon increasing the size of the subspace, the error decreases, okay? Because we're just obtaining a more expressive representation of the ground state wave function. But not only did we look at energetics, we also looked at other relevant physical quantities of the model. And in particular, we focused on spin-spin pairwise correlation functions. This describes how the spins of the systems respond to a particular state of the spin in the impurity, and how those correlations decay over distance. Here we are showing this spin-spin pairwise correlation functions for different values of the Hubbard on-site repulsion U. The blue color points correspond to the density matrix renormalization group results, and the white crosses correspond to the SKQD results that we obtained from our quantum experiments. And as you can see, there's extremely good agreement in the description of these pairwise correlation functions, which showed that sample-based Krylov quantum diagonalization could describe very accurately the ground state properties of the single impurity Anderson model. I would like to end this presentation by highlighting that all of the codes and tools can be found as part of the Qiskit add-on for sample-based quantum diagonalization. Everything is open source, so you can take a look at the code. And not only is it open source, but we also took some time to put together some tutorials to show you how to run sample-based quantum diagonalization and also sample-based Krylov quantum diagonalization. As I mentioned before, this is an open source project. It's on GitHub, so you can request extra features and so on. And I would like to end by summarizing that quantum-centric supercomputing, and in particular sample-based quantum diagonalization, enables realistic applications for chemistry and materials in today's quantum processors. We use classical distributed computing to process big data, while quantum is in charge of executing a few large quantum circuits, which is what it does best. This allowed us to simulate molecules up to 77 qubits and 3,500 2-qubit gates, and Hamiltonians related to materials up to 85 qubits and 6,000 2-qubit gates. And these systems are well beyond the reach of brute force classical simulations or exact diagonalization. And in the single impurity Anderson model, we showed that on a system that is well beyond the reach of exact diagonalization, we were obtaining very accurate results. For SKQD, we have a proof that shows that there's efficient convergence to the true ground state energy with a number of quantum circuits and number of samples collected from each circuit. And something that I have been highlighting throughout this presentation is that both sample-based quantum diagonalization and its Krylov version work best when the ground state is supported in a polynomial number of computational basis states. But beyond that assumption, these methods can be as heuristic methods, where the increase of the subspace dimension can give us an idea of how well the method is performing or will perform, without knowing whether the true ground state is sparse or not. And the last thing that I wanted to mention is that in sample-based quantum diagonalization, we are processing quantum data at the individual sample level. So to some extent, this can be understood as doing the most expressive operations on the results from the quantum data to try to extract the most useful information out of them instead of just taking averages to compute expectation values. So with this, I would like to thank you very much for your attention, and I'll be happy to answer any questions you may have.